When simple mechanical systems are joined, a disturbance in one will pass on to the next. When any stable mechanical system is disturbed, nature's response is simple harmonic motion. For a single oscillator, that's as far as it goes. But when oscillators are linked, from one to the next and to the next, a disturbance in one passes on to the next and continues on down the line. This is the essence of a mechanical wave. Sometimes individual mechanical oscillators are easy to discern. In other cases, the wave itself is easier to see than the individual oscillators. Perhaps more surprising, waves propagate not only along the surface of water, but even through the interior of a crystalline solid. A disturbance's speed depends on the medium through which it passes, and on the connection between one bit of matter and the next. If the linkage is weak, the disturbance passes slowly. If it's strong, the disturbance travels rapidly. But no matter the speed or the medium, water, air, or even a solid, all waves that propagate through any medium are called mechanical waves. Mechanical waves, or impulses, pass through a crystal from atom to atom because each atom is bound to an equilibrium position by electrical forces. When disturbed, they act mechanically, exactly like masses connected by springs. When an impulse moves through a system, no single oscillator goes very far, but the disturbance moves right along. Sometimes mechanical oscillations can be more moving than disturbing. It can be art as well as science, and it can be enjoyed as both. Musical instruments send continuous waves through the air that can be visualized as well as heard. Masses connected by springs may not look like beautiful music, but the principle is the same. And it can be described using a few handy terms. Each wave has an amplitude, the size of the disturbance, which is preserved as the wave moves along. It also has a definite time for each complete cycle, called the period. The inverse of the period is called the frequency. The tone of music depends on its frequency. The higher the frequency, the higher the tone or pitch of the sound. And the loudness of music depends on the amplitude. But no matter how loud, sounds are always on the move. And regardless of pitch or loudness, all sound travels through the air at exactly the same speed. If it didn't, every listener would hear a different performance. Whether it's short and sweet or loud and long, every wave has a definite distance from one compression to the next, called the wavelength. The wavelength equals the period times the speed of the wave. Or in other words, frequency times wavelength equals speed. Lower frequency generates a longer wavelength, but the speed remains the same. For sound waves in air, the speed is always the same, regardless of the frequency, the wavelength, or even the amplitude. But in this world, all waves don't get an even break. Sound and water waves travel at different speeds. And unlike sound waves, water waves can travel at speeds different from each other. At a considerable distance from a continent, way out there in the deep blue sea, long waves travel faster than short ones. But closer to the shore, waves travel together. And no matter their length, all waves decrease in speed as they approach the shore. In the mechanics of waves, that's the long and the short of it. Because on land, or at sea, in fact anywhere at all mechanical waves follow the same basic principles. Wherever anything makes waves, harmonic oscillators respond and then spring back. The oscillators are linked in such a way that every cycle of one excites the oscillator beside it.